for correlation. So this adjustment is based on this phenomenon that as you have very, very small sample sizes, you necessarily get a correlation, and it's being adjusted here. So at a sample size of 25, there's still a pretty big adjustment. And as I mentioned, once you get over 100, it looks pretty small. The standard error of the estimate, so this is the amount of error associated with the regression analysis in terms of predicting a particular value. And in this case, I'm almost positive, I haven't looked under the hood in this SPSS algorithm, but this standard error of the estimate is associated strictly with this model, and therefore would be accurate only for X values of 13.56. As you try to predict what a person's earnings would be based on their education of, say, 11 or 10 or 8, as you deviate from the actual mean in the model, this standard error of the estimate will not be accurate anymore. Anyway, that's kind of advanced and technical, and maybe I'll do a separate video in more detail about that. But this standard error of the estimate is, I'm almost positive, is strictly accurate for the model, and that by implication the mean of the X value, not for the other values. Here's the ANOVA table, which is basically telling us, is this correlation of 0.423 statistically significant? And we got an F value of 5.00, and it's statistically significant. But we also had a statistically significant value here that was estimated by the Pearson correlation approach, which is 0.018. So that's slightly different approaches to estimating the statistical significance of the model. We've got the coefficient value here, and this is where the real pertinent elements of the analysis is, particularly if we've already done a correlation analysis and we know there's a correlation. Well, that standardized beta over here, 0.423, is in fact the correlation between education and earnings. It's just repeated, and we have the statistical significance associated with this standardized beta weight based on the t-distribution, which is 0.035. So we know the correlation is statistically significant, but we do not know yet whether what 1 unit increase in education, so 1 extra year, how much extra can we expect on average a person to earn on a weekly basis, and that value is here. This unstandardized coefficient right here, B or beta, unstandardized beta, is 57.93. So if you increase your education by 1 year from 11 years to 12 years, you expect on average a almost $58 increase in earnings. This is again back in the 90s, if I'm not mistaken. It'd be great if somebody knew some study that's been published recently on the correlation between education and earnings, and please send it to me and I'll simulate the data so that we have more accurate estimates for 2011. But in the time period that this was based on, which I think is the late 90s, an extra $58 a week doesn't sound like very much, even by the standards back in the 90s, late 90s. Now here we have the intercept, and SPSS for whatever reason calls it the constant. And the constant, or the intercept, is the value of y, so the value of weekly earnings when x is 0. And I especially like this example for linear regression because this is obviously a nonsensical value. This suggests that if you have 0 education, you would earn negative $240 a week. So how you could earn negative values, does that mean that you're spending up your credit cards and you're borrowing money? I don't know. But there are simply no values associated in the data set. There are no values in this data set that correspond to an x value of 0. In fact, if we look at the scatter plot between education and earnings, we can see that earnings, now that I want to get that into the y-axis, predictor variable x. So if we look at the scatter plot, which you should always do anyway, here's the actual scatter plot between education and earnings, and we can see that in fact there is no, so the lowest is something like 8, and the the intercept value is trying to tell us, well, how much would someone earn if the